Yeah, good afternoon, everybody. Uh, it's a pleasure to be here. I was following this morning all the sessions. I'm particularly impressed how you can stand so many hours in front of a computer. I'm already bored, I tell you. But okay, I will do my best to be quick at least. Okay, we are talking about the geopolymer now. I hope to find out a way to share my screen with you. So probably this one. Yes.
Hopefully,
Uh,
with your geopolymer, we can resolve some of us that have been starting to corrode here, as this is our last session after we have been bombarding them with quite a few um, intense sessions the past 3 days. So I think your lightweight material will hopefully illuminate us.
okay, just give me a feedback. Do you see the presentation?
Yes, yes, you're set.
Oh, perfect. So, geopolymers, speaking about a little bit of chemistry after the launch break is fantastic. So keep everybody up and running. First of all, geopolymer, it is a very old word. I mean, it was this word was invented more about 50 years ago. Anyway, I'm pretty sure that few of you has ever met them because even if there are some products, okay, specifically this morning was mentioned products like Geolite that sound a little bit like geopolymer. It is not. It is a very good name, but has nothing to do with the geopolymer technology. That just to make it clear. So. Uh, the geopolymer science was started by this French scientist, Joseph Davidovits, many years ago. And you'll find a lot of information at this website I wrote, geopolymer.org. And this scientist was a polymer scientist. What does it mean? It was dealing with plastics, rubbers, and all this kind of stuff. Varnishes, polymers are around us, particularly organic polymers. And the problem was that all these kind of polymers was burning. So the fire was a big issue for big cities like Paris or London or Los Angeles, where he works also. So he was searching the way to build a polymer that do not burn, that is fire-proof, fire-resistant. And the conclusion was that cannot be. Organic polymer cannot be in any way fire-resistant. However, he found out a way, and we're going to see that way to have an inorganic polymer. Okay. In the beginning, in the beginning of the 70s, officially at the end of the 70s, then during his study, he discovered also that a lot of geopolymer was already present on buildings like the pyramids, for example, or in other places in the world in archaeology. So how he know that? He was going into this place and pick up some samples of these stones and analyze it with modern technologies, spectroscopy or other microscopes and so. And you can understand easily that in the beginning, he was treated like a kind of theory of conspiracy, because all these people studying this old building, ancient building, saying that yes, the slave was carrying for the quarry, the stones, and there is a lot of thoughts about it, and they treat him. All the scientists, they treat him as a conspiracy theory man, and it was in the beginning the study on geopolymers was very limited. But what's happened next? It's happened that if you look now at the number of publication on the, okay, I grab one of the major sites for concrete that I normally use, this Science Direct, but you can pick any other one. You see that recently, in the last 10-15 years, the studies and the scientists studying geopolymer has grown in a dramatic way. We are last year was nearly 4,000 articles published, and this year we are already more than 100, and February is not finished yet. So the interest on this technology has taken off definitely. So what is a geopolymer and why you should care? First of all, it's a polymer. It's a polymer. What does it mean? A polymer is a material that consists of very large molecules, or we say macromolecules, that are constituted by many repeating subunits. So you get a subunit that repeats, and it is called monomer. And it is very common in plastic, like polystyrene, and also paints, resin. Even if they exist natural polymers or biopolymers, if you want, such our DNA, what we are made from, the DNA, it is a polymer. Proteins are polymer, okay? And all these organic polymer has in common a group that has a chemically carbon inside, and that's why they are calling organic polymer. But in this case, the second property, it is that geopolymer is mineral. So it has no carbon or no water or no hydrogen inside. It substitute, for example, aluminum with carbon in the chain of the polymer, and that so you can obtain something more similar to a rock than to a plastic, okay? And this is the basis for any geopolymeric product, because yes, we will see in a next slide that what I described to you is called precursor, that it is a kind of binder, if you imagine concrete, and then you can add different stuff to obtain different kind of products. But okay, make it simple. What is a geopolymer? How is made in reality? One of the way to make geopolymers, this is one of the way we follow here at EcoBeton, is to take a clay that is a product from the soil, basically, kaolin in this case, and a silicate together. Kaolin is a clay that you can find all over. It's sourced globally. The production centers, there are a lot of it in United States, Brazil, China, Germany as well, India, Africa, and so on. And it is extracted via an open pit. And that means it's a mining techniques, okay? And it's already used in a lot of applications such as paper or ceramics or paints or pharmaceutical industry. Okay, and sodium silicate or potassium silicate, it's one of the largest product in Europe, because also it's based on silicium, so that means sand, and the earth is rich of sand all over the world. And it's followed the same path of glass production. in fact, is also called water glass, and it is fully mineral, and rich in silicium, of course. The proper proportion and the proper version of these two components make the base, the precursor of a geopolymer. And what you can do then with that? You can cast objects like vases, following Professor Davidovits is convinced that ancient vases was casted like this. Or you can do fiber composites. What does it mean? For example, you can have carbon fiber composites or glass fiber composites to making such objects. For example, if you think about Formula One racing cars, the Ferrari, McLaren, and so. The final part of the car where the fumes are going out, the exhaustion tube, was made in a carbon composites. But the problem is that the higher is the temperature of the fumes that go out of the engine, the better is for the car, for the performances of the car. So carbon composites can stand only up to 500-600 degrees Celsius maximum. So nowadays, all the cars in Formula One racing competition has this part made on geopolymers. It's a French company who is making it, okay, and they have this system. Or you can have paints, or even dental cements. When you go to the dentist and they say, I'm going to put some cement on your tooth, this is a geopolymer, because human bones are very, very similar. They are geopolymers, actually. It seems they are very, very similar in structure, so it's very compatible. And of course, you can do what we are more interested in, so that means concrete and mortar. Not in Europe, but in Australia, for example, more than 10 years ago, they did the full airport realized on geopolymer concrete. So I'm talking about buildings and also all the landing tracks and the parking structure of the airplanes. You find everything on geopolymer.org if you are interested in it. What are the properties of geopolymers? Yes, today everybody say sustainable and eco-friendly, and of course everybody is pushing that way, and they are achieving some results. Here we are talking. There is no cement inside. There is no water inside. We are talking about a savings of about 80 to 90% of CO2 footprint, and not only of footprint, also of other aspects. Okay, and he has a high chemical resistance. You can think about geopolymer more or less like a ceramic product. So it is completely suitable for high chemical. And why we are so interested in it? It is because at the end, the major enemy of concrete, it's carbonation or chloride penetration, and they are attacking chemically the concrete. And yes, it is 100% fireproof. So also the concrete, it seems fireproof, but this is not only fireproof, it's also fire resistant. Concrete, if you burn concrete, since there is water inside, because it's an hydraulic binder, after some 100 to 100 degrees, the bond with water starts to break. And after a fire, concrete is completely destroyed. Okay, geopolymer are not. They can resist up to. We arrived to 1200, so 1200 degrees C without any damage, just to have an idea. And the mechanical properties are very high. We can consider, usually depends on formulation, but they are double than normal concrete, to have an idea. Okay. So what you can do with geopolymer, it's you can have a resin, for example. We developed this resin to make electrical insulation. Some elements that needs to be insulated. This is a coil for induction, and they use resin, but you understand that organic resin, after when you are about 300, 400 degrees C, start to burn and to make fumes and so on. Or you can do composite material. This is an artist, French artist, that is doing a lot of stuff with our products. You can have foam also, and this is a particularly interesting field of application. All the scientists are working on this foam because you can have insulation that does not burn at all. You know how big issue, how big discover. Still, there's not mature, but everybody is following this one. And then concrete, of course, it looks also very similar to normal concrete. You can use it to do thermal insulation, so to protect stuff from heat. For example, in ceramics, when they cast iron, for example, to contain a liquid metal, we use nowadays geopolymer. There is a project for planes, for make fabric for tissue. I mean, for the airplanes. To reduce the flammability of all the components. This is already some years that this, and I believe some companies in the United States already start with that one. And you can use it to encapsulate any kind of stuff, because geopoly is very stable from the chemical point of view. So you use for waste treatment, even nuclear waste treatment. There are some specialized company who is doing that with geopolymer. So pretty wide application, right? What I'm going to present to you today, before it's too late, because I see is running, it is using geopolymers for restoration, retrofitting, you can call it, the restoration of concrete in historical modern concrete of last century. The product is called Geoteria, and we want to develop, we are at a very good point, but a repair that can last longer than traditional repairings. Because what we notice is that once you repair the concrete, that reparation do not stay as long as the original concrete. It has a lifespan. The reparation lifespan is very short. Okay, to significantly lower the footprint, of course, and to have something that you can apply at any thickness. One of the property of geopolymer, there is no water inside. It's not a replacement of a cement. It's another thing. Cement is another mixture, and geopolymer is an order, from a chemical point of view, it's an order structure. So it's completely another thing. It is better that you think of the geopolymer more like a plastic, if you want, than a cement. And so there is no shrinkage. There is no shrinkage, and this allows you to apply from 1 millimeter to 20 centimeters in in a row without because shrinkage is another big issue for concrete reparation, and of course the ability to reproduce texture and color that you want. We are in the field of restoration, and these objects are very good. We don't want to patch them like Arlecchino way, okay? So we were very lucky because we have the possibility to test the product on real concrete from last century. I'm talking about this concrete from Villaggio Eni, that is nearby the Olympic area. And it is a project from architect Gellner that was one of the, let's say, friends of Scarpa in the Venice team. Okay, in fact, Scarpa did a church over there and other things, and very luckily. Okay, not luckily for the place, there was a storm many years ago called Storm Vaya that was demolishing some structure, okay, some minor structure. We are talking about the parking area, if I remember well. And so we was seeking, we know that the concrete was there, we have to deep seek under a lot of trees and stuff, and then we got the possibility to take this concrete to make the test directly on top of it. And that is very important because, laboratory is very easy. Laboratory will always function, or not always, but will easily function. Make a product function on the original concrete, it is a great opportunity. So what we did was a preliminary test. We start with the phenolphthalein test, that is this purple stuff that you see on the sample, and this measures the depth of carbonation. Carbonation, I told you before, is one of the biggest enemy of rebar, steel rebar in concrete. And it is the responsible of starting a chain that led the concrete to destroy, basically, because the rust is going to grow the rebar and then make pressure on the surface and then act what we call spalling of the concrete, okay? So when you spray, very easy, you spray this product, and where is purple means the concrete still have a very high pH, so the rebar are protected. Where is clear without no coloring, the rebar are not protected. And you see in this picture, we got 4 rebars, and all 4 of that are, I don't know if I able with the mouse. No, okay, doesn't matter. All the 4 rebar are outside this one. Then we do a porosity test and then a petrographic analysis. Why porosity test? It is so important because the pore volume here, I put you a microscope pictures and you see the void. This is the pores, because concrete, when you make concrete, there is a lot of water inside, and then water eventually evaporates from concrete and leave a hole, and that is related to durability of everything, because through that holes, all the pollution, carbonation, chlorides, everything is penetrating and destroying concrete. So knowing the porosity is fundamental to do a reparation. And then also this morning, the first professor this morning was showing you something about petrography and analysis. So I'm going fast because I see that the time is going and I don't want to keep it. So it's not a matter of to have a good products. it is a matter to have a good system, because very often we observe that after a reparation, the reparation after some years detach from the original concrete, and is not detaching in the interface. It is detaching below the interface. So some part of the original material is pulling off, you know. Why? Because of poor substrate preparation. You have to reduce in porosity, you have to improve the bonding. Usually you have to restore the pH, realkalinization. We don't need with geopolymers, but this is a good suggestion for concrete reparation. So we choose a deep penetrating mineral sealer for doing that. Then you have to take care of rebar, because of course rebar are probably already rusted when you meet it. So you got basically three strategy. The first one is to passivating the rebar with paints. It's a very old technique. Nowadays, almost all the producer prefer to use passivating mortars. So to use mortars that already has this passivating stuff inside the mix. What we prefer in any case is to use rust converters. So to transform the existing rust in a stable layer. So no further corrosion will go on it. Then you go to choose the right aggregates and to match the color and to do all this kind of stuff. And then you have to monitor the results. And this is exactly what we are going to do this summer. So we got our concrete from last century. We got the geopolymer. We will apply it and then monitor the results in time. And what does it mean? It means make a pull-off test. On the picture you see, what does it mean? You attach some small circles, and then with the machine you make a force to extract it, and then you measure how much how the bond it is, and you have to look at cracking, at shrinkage, at everything that happens in the interface, or even the color change, because we want to keep the color stable and as much as possible matching the original color, for example. And what's happened after freeze-thaw cycle, and what's happened with porosity and water absorption, for all the reasons that I told you before. Sorry if I went a little bit quickly. I hope I'm still in the time.
Yes, don't worry.
That's it.